Okay. Just a couple reminders here that so you have homework due tomorrow at 2 p.m. on counting, section 2.3, and the lab 2 is due. Do you have questions? Oh, and also there's a key to homework 2.1 and homework 2.2 there as well. Yes?
We have some questions over
Okay, what's your question then?
I have a couple, but
Okay.
the problem A.
Can you read the prompt for me?
It's the marriage one, and you're sitting down in an empty seat.
It's the marriage one, and you're sitting down in a seat.
Yeah, there's 6 seats available, 3 married couples.
Okay. What you could do is think back to the Bible verse, or maybe to a wedding ceremony, that the two shall become one. So treat a couple as one. So you can put, I don't know, J and P in the first two places, then how many ways can you see the other four?
So are you saying couples are always together?
No, you're just randomly putting 6 people on these seats, and then you're trying to figure out what's the number of probability that, like, different situations that people will sit together if they're married.
Okay. So there's 2 options for the first one.
Yeah.
For factorial.
Right, so 4 times 3 times 2 for the second one, right?
Right.
Okay, for the second problem then, what's it ask?
What's the probability that Jim and Paula end up sitting next to each other?
That, what is their names?
Jim and Paula.
Jim and Paul sit next to each other. And this is where I say you can treat these as one couple or as one entity. Treat them as a union, as one, the way that perhaps God has made them to be. How many ways do you have now then left?
Well, they can either be in the first 2, or they can be
No, just treat them as one. Then how many spots do we have left?
still 4.
So we have 5 spots altogether, right?
Yeah.
So how many ways can you arrange 5 spots?
Actually,
And then you'd have to take into account that you could sit those 2 people in 2 different ways. So I guess that's my suggestion, is sort of, when you're doing these problems, think of them, the couple as one, and then think about the number of seats that you could have left then.
Okay.
Okay, what's another question that you have?
105, part B.
And that, can you read that question then?
This is the birthday one. Where
Oh,
you
yeah.
put 10 people. It says with K replacing 10 in part A, what is the smallest K for which there's at least a 50-50 chance that 2 people will have the same number?
Right, so that one you're gonna have to use either a spreadsheet or maybe your calculator to try different values for that one.
So,
I mean, you could set up, you probably already use some sort of permutation, so you could set that up and then redo the re-entry on your Texas Instrument calculator and then change the values that
I
way.
guess I don't know what the question's asking. Like, what's,
So did you do the first one, like if you have 5 people, what's the probability that 5 people have the same birthday?
10, but
10,
all
yeah.
have different birthdays.
They all have different birthdays. So this time it's, instead of 10, you're trying to do like 100 or 150 or 75 or so forth. Tegan? then Josh?
Where's the K, what's the K supposed to be?
K, I imagine, is the number of people that you have in the room.
I didn't, you're right, plus.
Oh, with K replacing the number 10.
Yeah,
Wait,
yeah.
there's just double on it.
Oh.
So it'd be, yeah, it's just, oh, yeah, literally just times 2.
Okay.
So then you have to find the number of people that have to be in the room to where there's at least a 50 chance that 2 people have the same birthday.
Yeah, yeah.
How do you take into account 2 or more? Like,
Well, that's why you may want to take the complement, right? So maybe you want to figure out the probability that no one has the same birthday. And then get that below a certain threshold.
so a 50-50 chance that no one has?
That no 2 people have the same birthday. That may be what you want to do. Because then you take the complement, then you have at least 2, or these people might have the same birthday on August 17th, these people might have the same birthday on March 12th. Okay? Yes?
How do you go about part C of problem A, which is what are the odds that any of the couples sit next to each other?
I would put them together and count them.
Okay.
And then I would use the inclusion-exclusion principle. You know, that 3 diagram thing? And so figure out the probability that 1 couple sits next to each other, and then figure out the probability that 2 couples sit next to each other, and then find the probability that 3 couples sit next to each other.
Is there a way you could do it where you find where no couples sit next to each other and take a complement? Or is that harder?
You could do that too. That is a way that you can do it. You just asked me how I would do it.
Okay,
so.
yeah, all right.
Okay, if you have other questions, you can come by and stop by my office or whatever. So let's go ahead to section 2.4. And the big question here is another philosophical question that we have. Did you look over section 2.4? No, that's not the big philosophical question. You should circle that, yes or no, whether you did that or not in preparation. Remember, that's kind of our, you have some expectations for me, I have some expectations for you. The question is, when I learn new information about a prior belief, what is the probability that I will change my mind? So this is found on page 29. So if I learn information about a prior belief, how likely is it that I will change my mind? Should roll the dice. Anybody want to volunteer so I don't have to make a call on people? Now let's pick a number between 1 and 117. 50. Jonathan, what about you? If you find some information, how likely is it that you will change your mind?
Are you asking for like a number or just some thoughts?
You can give just some thoughts. We don't have to give a number always in this class.
Yeah, I like to think that I keep an open mind, especially with potentially new information that might go against something I believed before, but I don't know in actuality how often that really changes what I think.
Sure. There is something called confirmation bias, right? That we take in those things that support our belief or our views and sort of dismiss those things that are out. Jeff, what about you? What kind of person are you?
I mean, I would apportion my confidence and try to apportion my confidence in accordance with the strength of the evidence. So if new evidence came along, then I would like to just reduce my confidence or switch belief.
Okay. Of course, it depends on what we're talking about, whether it's talking about the best social media site or if it's talking about my deep religious faith. That also might take into account as far as how important it is that I do so. But anyway, we're going to talk about this. This is We have a jury of jury of 3 persons randomly chosen from 9 people, 6 men and 3 women. We found that the probability of exactly 2 women being selected is about 21.4%. But now suppose that the jury is required to have at least 1 woman and 1 man. Given this additional information, what is our revised value for the probability the jury has 2 women and 1 man? Would we go higher, lower, or stay the same? So just a quick answer here. How many go with higher? Is that our probability we would be higher? Nobody? Oh, 1, 2. How many will go with lower? A couple. How many will stays the same? Okay, I might have asked the question too quickly for you to figure this out. So let's try another example. I think there's about 20% of Taylor students are athletes. Okay? So you take a randomly selected person at Taylor, student at Taylor, there's a 1 in 5 chance that that student's an athlete. But now, what if I say that that student is from Bergwall? Would you change your probability?
Yeah.
Yes.
Yeah.
Okay. So you're learning new information.
Because there's already like information correlated to it.
All right. So this is the situation. One event is given that it's known to occur. In this case, at least 1 of each, and we want to find the probability of another event, A equals 2 women and 1 man. So the notation here, and this is a big notation, the probability of A given B. So we're given this situation, we want to know what's the probability of A coming out. So the sample space is no longer all of S, it's smaller. So let's just draw our good old Venn diagram here. So rather than finding the probability of A given in the whole subspace, or the whole sample space, what we would do is we would only want this now as becomes our sample space of B, and we want to know what the proportion is of A within that sample space. So in some sense, we're restricting the sample space down and now trying to figure out the proportion of A given B. All right, so that's the picture that we have there. And so now we have to define this. What is this red and blue area? How could we represent that by? Yeah, so that's the probability of A intersect B. And then what's the blue area? Probability of B. So this is, like I told you about the axioms of probability, you know, totality, non-negativity, disjoint, they're disjointed, you can sum them up. This is another formula that you want to know, like 6 times 7 is 42. Yes?
Why are you dividing by the probability?
Because now we've restricted it to a smaller area.
Oh, so that's now your sample space.
Yeah, so instead of 2,000 students
Yeah.
in Bergwall, 210. How many students are in Bergwall?
200.
Okay, let's say 200, and now you're taking the athletes from there. Now, why must we assume that the probability is bigger than 0, other than the formula divided by 0?
Because you're given it.
Yeah, so if I'm given keep going. I should not tell you the entire answer. What would it mean that the probability of B is 0?
It's negligible, so it doesn't matter.
Or impossible, right?
Yeah, yeah.
Right, so then we're not even talking about a real situation, right? So, given that I could beat Michael Jordan in a one-on-one basketball game, then what's the probability I'll be the next president of the United States? Or what's the probability that I'll give an exam, an easy exam? I mean, so these are kind of situations that I could say, you know, I don't know anything. So let's go ahead and take a look at the probability of 2, at least 1 of each. Remember that what we're doing here is writing this, the probability of 2 female and 1 man, given the probability of at least one of each. Yeah, I'm still on the screen. That's good. So in the numerator, we have, from this up here, 18 out of 84. And so we could either have 2 female and 1 male, or what's our other possibility? If we have to have at least one of each, then we could have 2 female. Yeah, so 2 males and 1 female. What does that say? 2 males and 1 female. So this would be 6 choose 2, 3 choose 1, over 9 choose 3. And choose 2, 6 times 5 divided by 2 is 15. Yeah, so 45 over 84. So 18 over 63, or 2/7 probability. So given an additional bit of information, our probability has changed. Now, there are some exact counter... just like to get going. It's such a great stuff today. Forget to pause to see if you have any questions about that.
I'm confused how you got the questions.
Well, up above, we do have the 18 out of 84, right? That was given to you up there, right? And that was for 2 females and 1 male. And then I also have to take out, well, how many ways could I have at least 1 male and 1 female? Either I have 2 females and 1 male, or 1 female and 2, the other one. And so I calculated that probability.
So that's why you divide by those 2.
Yeah, because I have to add these 2 together, and I get 63 out of 84. And so 18 over 63, divide both by 9, I get 2/7. Does that answer your question then? Okay. Now, there are exact counterparts for the probabilities that you've had before. So for example, the probability of A complement given B is equal to 1 minus the probability of A given B. Or the probability of A union B given C is the probability of A given C plus the probability of B given C minus what thing would fill in the blank after this? Yeah, so A intersect B given C. So you're just adding the given C to our good old formulas. And there's all the other formulas as well. Yeah.
Could we go what A intercept B gives C?
Well, you know that the probability of A union B is the probability of A plus the probability of C minus the probability of A intersect B. That's just our unconditional probabilities that we should know. Yes, Jeff?
So in terms of just order of operations, you don't need to put parentheses around the B given C.
Oh, yeah. And that's really an unfortunate part of this kind of notation, that if you, it is kind of difficult to know, is it A union B given C, but the given sort of takes precedence. You know, the left side is what you're calculating, and the given on the right side. If you think you need it just to make it clear for your reader, you would put the parentheses around. Okay, now, this is the general multiplication rule, another very important rule. So the situation is, hey, I know the probability of A given B. And I know the probability of B. I know the probability of who is in, given this, we're in Birdwall, I know what the probability of them being athletes. And I also know what the probability in Birdwall, on the basis of the entire student population, I want to know is what the probability of being an athlete and being in Birdwall. So the rule is, well, just use, if this is equal to the probability of A intersect B over the probability of B, then I know that the probability of A intersect B is equal to probability of B times the probability of A given B. And if you think about it, there's another way that I could write this. Which did I write over there? I guess I wrote a probability of B times the probability of A given B. What's another way that I could write this? Yeah, except for you probably can't read. Yeah, so you could do it in either order.
Is that supposed to be probability of A?
Say it again a little louder.
Is that supposed to be probability of A?
Yeah, I tried to write this over to make this a B.
So then what's that last part?
It's another way of thinking about it. Instead of picking A first, or B first, I could pick A first.
So take out that middle part, it's still probability of A intersect B equals probability of A minus probability of B.
No, that's a multiplication. These are dots. This is multiplication.
Okay.
Make my dot a little bit better. So let's revisit our case where the first two jurors picked are both female. Remember, we had 3 females out of 9. Okay, so what's the probability my first juror is a female? 3 out of 9. Now, given that the first is a female, what's the probability the second is a female? 2 out of 8. And so 6 out of 72, or 1/12. So again, this part right here is the probability that the first is a female, and the second one is the probability of female given the first is a female. All right, so the general multiplication rule then is probability of A times the probability of B given A times the probability of C given A intersect B. And Jeff, this is kind of where it gets a little tricky as far as C given A intersect B, but we're going all the way across. So C given A intersect B. And
There'd be parentheses around the.
yeah,
intersection.
like the intersection part would be kind of a good thing to use. But kind of think about this. What's the probability that the first is first that I pick is a female? 3 out of 9. All right, given that the first is a female, what's the probability the second is a female? And given that the first 2 are females, what's the probability the third one is a female? 1 out of 7. And so I get 6 out of 504, I think it is. And 1 out of 84, I believe. Okay.
Does that say, just to bump that, does that say probability of C given A intersect B?
Yeah, that's right. That's right. All right.